Thank you very much for this kind introduction. I'm going to try to run through my slides in the next 40 minutes. So the title today is Connecting with Purpose. And I'm going to try to convince you of this, hopefully, near future, where everything's connected automatically, and AI is an integral part of this connected world. For that to happen, to me, we need innovations that are beyond what we've been able to do in 5G. That's what I'm calling the 6G revolution, or the next wireless revolution. To me, and to a lot of us in academia as well as industry, those innovations effectively can be grouped into two. What you see on the right hand is convergent connectivity. What I'm calling convergent connectivity is devices and networks that are used for more than one function. We're already seeing this, of course, with our everyday use of the cellular technology. However, what we're suggesting for next generation is to go beyond this separate optimization of communication and computing, separate optimization of sensing and communications, and move to a paradigm where we think as a whole of the network and redesign in the way that's best for all of these functionalities. And with what's coming with next generation, the open architectures, we are for the first time hopeful that academic papers can actually make an impact beyond what they have been able to with a, let's say, less delay than 20 years in industry standards as well. What you see on the left is what I'm calling human-centric connectivity, and that's to look for new metrics to evaluate these systems, these networked systems, whether it be usefulness metrics for the information or for the network itself, whether it would be metrics specifically in terms of executing a given task, or whether it's semantic communications. So I'm going to try to give you some examples in most of these today. We have billions of edge devices. We have, it's not like the number of devices connected or that need connectivity is going to decrease, quite the opposite. So we might as well make use of these devices and how they connect to the network. So for example, we can use them to learn, to execute machine learning tasks. For example, training a possibly large machine learning model, as well as inference and so on. So model training using data, local data at each device, and then collaboratively coming to one or more models is a rather large direction in machine learning, still as part of distributed learning, as was mentioned before. And that's something that has been going on already, say, on our cell phones. The challenges, of course, of such a model is, again, there can be potentially a very large communication overhead. Trying to do this, if we try to do this as we're doing now, that is agnostic to the underlying medium. How this was first formulated and is being currently run is agnostic to the medium, meaning there's a noiseless bit pipe underneath each communication link. That, of course, means more communication overhead. Also, even though such distributed collaborative training approaches have been proposed with the main goal of preserving privacy, by preserving data at local devices. In fact, because it's an iterative process, again, as was mentioned by the previous keynote, it is an iterative process that could take hundreds of iterations, which means you're processing and processing data from the local device and then communicating some function of that to a central unit. So that could mean privacy leakage as well. So what I want to tell you about is both of these concerns we can actually address by communicating wirelessly, and more importantly, realizing that we're communicating wirelessly and designing accordingly. So I call this connecting for learning. So we could do collaborative training conducted in the wireless medium, meaning a joint cross-layer approach of designing the physical layer and the machine learning process. And in particular, we can address the communication overhead by utilizing the medium itself to do the aggregation, rather than having thousands of channels in which we will need to communicate model updates. We can actually let the air do the aggregation by simultaneous transmissions. We can also, as we'll see shortly, leverage the fact that we're in the broadcast medium to improve privacy and alleviate the privacy concerns. So the first one is an approach that was invented 4 years ago called over-the-air federated learning. And essentially, as I mentioned, what we're doing is we're doing simultaneous transmissions of all of the model updates, of course, suitably tailored, so that they can nicely aggregate over the air, and you basically get an aggregated average model at the base station, or as machine learning community calls, parameter server. It is a communication-efficient method, and our approach to this was a little bit different than what was done in the conventional systems, where computation and communication was, in a sense, addressed separately or optimized separately. So you have a computation problem, you have a machine learning problem, which is essentially, in this instance, is minimizing an average loss function. So you design an algorithm to accomplish that, and then underlying, there's a wireless channel, which you can also optimize, for example, by minimizing the MSE. So that's sort of the, if you like, the conventional approach. The approach that we have taken was a little different. We started with the learning problem itself, analyzed the learning problem, looked into the factors that impact the convergence of that learning problem due to the wireless physical layer, and went back and designed the physical layer. Okay, so that's what I'm calling the cross-layer approach. Communication impacts computing, computing impacts communication. This sort of approach, because we're looking at a general setup, could actually address having terminals that have heterogeneous capabilities in terms of computing, in terms of power resources. Because everything's going to be optimized that way, we can actually utilize devices that may have asymmetric capabilities in terms of data they collect, in terms of powers that they can use, and in terms of the computation steps that they can provide. Again, certainly an approach that could move into the future, especially because we have to be thinking about the energy costs of these computations in the future. The next step that we can introduce in a 6G and beyond type of future is learning the lesson from this design, where clearly the quality of channel impacts the learning directly, going back and seeing whether we can make the channels better. And this is something that we've done previously with sort of less adaptive systems, but we've tried putting in lots of antennas to try to make channels better, right? We've tried including variations of the channel into our design so we can get better performance. This is similar and has been very well received in this community, and that's to include new network elements in the form of intelligent surfaces. That way you can, to a degree, program your channel and have better communication. So now we're going to bring that, fold that into this framework and make learning better. Here is the first example is with a single reconfigurable intelligent surface, which could help in the learning performance. So we have called this algorithm RIS-assisted over-the-air adaptive resource allocation for federated learning, or ROR-Fed. And really what we're doing here is, it is a federated learning algorithm that's over the air, but it also includes this tilting of this RIS, which in each iteration, where you send your local updates up to the base station simultaneously, actually changes the channel in this case, in favor of one of the selected users, and that rotates between the users. So in essence, we're making the channel better every time we go, and that, of course, helps the system overall, the power, the computation, the convergence. So here's some experimental results. Our baseline are the state-of-the-art over-the-air federated learning with reflecting surfaces, or one reflecting surface included in the system. The reason why the baselines are not converging, this is actually a digit data set with 10 classes, so if you're getting 10% of learning performance, that's not learning. Ours, as you can see, the two algorithms are getting reasonably good accuracies. The reason for this is here we are addressing the fact that we're looking into a heterogeneous scenario. The data is heterogeneous at each device, non-IID, computation resources, the number of local steps of iterations that you have to do in each time you get a new model at each device is optimized, and the power is controlled and aligned. Okay? So we can go one more step, and we can actually personalize this model to accommodate the so-called personalized learning models. That's the next step in the machine learning community. You are collaboratively training not only for a common global model, but also personalize the models to each user or clusters of users. We can actually have portable small RIS devices that are associated with users and, in a sense, steer our channels in the best possible way for each user. So this is all physical layer design that most in this community are familiar with, but again, our objective is to make learning better. Here are some results, and again, the point I want to make here is that this actually here we have a non-convex objective. So it's a slightly more, let's say, challenging machine learning problem, machine learning model we're trying to train for. And what we're doing here is demonstrating the fact that if you were to distribute the resources that you have with respect to these reflecting surfaces from one giant one to many smaller ones that are serving each user, we're able to actually get better performance for the general model, but also for personalized models. All right. We can utilize physical layer for also improving privacy. I mentioned that these distributed collaborative training models, while providing some inherent privacy, will have a potential for privacy leakage. And the way to typically address this is having differential private learning with a typical mechanism, which we'll also use here, that includes adding noise to the models that you're sending, either at the receiving end or at the transmitting end, which is what we're going to do here. So adding noise to the models that you just updated is not a great idea in terms of accuracy, right? So if you make the models that you spend so much computation on to make better worse by adding noise, that actually delays your convergence. So if we could find mechanisms where we still use this notion of differential privacy, but perhaps with less sort of distortion that you're creating yourself, that's better. Okay, so that's what we're going to aim here. I call this connect to learn privately, utilizing differential privacy, but really in the context of naturally what's occurring at the wireless medium, if we can get away with it, that is the noise, and address perhaps enlisting a terminal to help us who's not doing learning, and therefore we're not actually, let's say, distorting our own learning models, but there's a separate terminal that could actually help us achieve this goal. All right, so here we're bringing an idea from so-called physical layer security that is quite old into this learning framework. All right, so this is differentially private over-the-air federated learning. Each edge user is going to send their models, and because we have the physical over-the-air federated learning, we'll actually have the noise added to the models over the air, and we won't need to distort ourselves. If we can get away with this and we have an analysis and a threshold for this, then we're good. If our privacy requirements are so strict that the naturally occurring noise is not going to be sufficient, then we can enlist, say, one of the users as a cooperative jammer in each round so they can provide the privacy guarantee that is needed. So that's the idea here. Again, requires, just like before, a well-designed power control algorithm for everything to work out. So I put here two numerical results. The one on the left is a privacy level that doesn't need the cooperative jammer. So the Gaussian noise in the system itself, in the channel itself, is going to be sufficient. The one on the right requires a participation of a terminal. And again, this could be an external terminal. This could be a terminal that chooses not to participate in that particular round. We can do a round robin between different users. Or it can be a terminal that is trying to do something else, for example, sensing. And so it's already going to send some signal to bounce off from a target, right? So that brings me to my next little segment, and that is to have multiple functionalities for the signals that we're actually sending. So a prime example of this is integrated sensing and communications, where we actually design waveforms for sensing and communication simultaneously, right? Which is clearly great for better spectrum efficiency, better spectrum usage, and hardware efficiency as well. But when you reuse things for multiple things, you are risking new security attacks. Right? You have a potential adversary as your sensing target that is actually receiving a signal that contains information. So whether it's a malicious one or an honest but curious one, it can try to decode the information in it, and therefore you must protect it. So one thing that, we've addressed this as a community, we've addressed these sort of security concerns in the physical layer and so on for quite some time, but perhaps the one that we haven't, as communication theorists, wireless communications people, haven't looked at is, in fact, the fact that you take an action at the transmitter that may be correlated with the channel can help you. This is something that the theory community has addressed to a degree. So for example, a physical movement of a transmitter is going to impact the channel, including a new element like an RAS will impact the channel, and that in turn could dictate how to better design the system that will actually provide you with security from such a sensing target. So here, if you work out the theory, it actually provides you with design insights. You treat the sensing target as an eavesdropper, and you utilize the fact that the transmitter will observe the reflections from your legitimate receiver as well as your sensing target, and you can adapt your actions accordingly. Okay? And if you work through this, you see that the sensing information that you get is actually helping you for doing better security in your communication. So that's where we see the synergy, and that's what the theory is telling you. Of course, completely in the nice asymptotic regime that theorists like, but it's not just there. You can actually do an analysis for practical networks with stringent latency constraints, and you can actually quantify how much you need to back off from capacity and still get this advantage. All right? So I hope I've been able to tell you so far about the importance of utilizing wireless resources in the most efficient manner possible. No matter how much more bandwidth we add to our next generation, there will always be a demand for more and more and more. And therefore, we always have to be finding ways to be more and more efficient. That brings me to the last part that I want to talk about, and that's connect to convey the meaning. The goal here is to move away from our conventional, as was mentioned at the beginning of the previous talk, our conventional designs of sending a digital sequence from one end to the other and replicating it asymptotically error-free. Instead, we're going to strive to convey the meaning of the messages at hand. Why would we want to do this? Efficiency, efficiency, efficiency. That should be the goal, the primary goal. If doing semantic communications provides you with a more efficient network design, that's when you go for that. Okay? So instead of mapping our messages to digital sequences, which we then code, put in the channel, modulate, and send, we're now going to be thinking semantically both at the transmitter and the receiver. The regular hand-drawn version of this fabulous AI-generated figure is this one. Okay? So the one up top we're familiar with. There's a transmitter, there's a physical channel in between, and there's a decoder, there's a receiver. we're now going to replace the transmitter and the receiver with their semantic versions. And we'll talk about what that means next. OK, so I want to start by calling attention to this paper. This is probably one of the most, I would say, impactful papers we worked on. And it was about 10 years ahead of its time. But that didn't stop us. With some difficulty, we have gotten it published in 2014. This is called Semantic Index Assignment. And if you look at the abstract, this is the first paper that actually talks about the semantic end-to-end measure in designing a communication system, in the modern times, that is. Okay? And the idea here is to look into the words, the messages that we are transmitting, and look for a mapping from those source words to what we're going to send through the channel in a manner that is semantics aware. In this example, what that simply meant was, after all the optimization and so on, what it ended up telling us was that if you have words that are semantically similar to one another, then you should map them to digital sequences that are close in terms of Hamming distance. The reason being very intuitive and simple. If you end up making a mistake at your receiver end, you probably will land on one of the neighboring code words. And so if that neighboring code word is something that actually is pretty much what you're looking for, then that should be enough. You should not need a retransmission. Okay? So very, very simple intuition that we have been successfully able to implement with 16 words. Okay? So the overall optimization problem is one that is computationally complex. And so you end up, trying. Remember, this is like 2012, right? There's no sort of machine learning anything yet. So, clearly an interesting, cute idea, academic, no impact, because clearly it's not scalable, right? Awesome. So then machine learning came. And when machine learning came, we realized, including in this community, that we can do a lot more utilizing machine learning algorithms, utilizing data-fueled architectures. And so semantic communications came back essentially following autoencoder-based wireless physical layer that has been introduced in 2017. I forgot to put that reference here. But at the end of the day, this is sort of the time where we all realize we can utilize deep learning for designing physical layer. Right? So if we can do that with sort of regular transmitter receiver, certainly we should be able to do that with this sort of new end-to-end metric and so on. All right. So our group's vision has also evolved, as I mentioned, from the first publication in 2014 to last year. We're now able to do a lot more thanks to the advances in machine learning and AI. In the sort of more model-based, or actually purely model-based formulation, we were simply utilizing text communications and borrowing sort of the state-of-the-art then, word taxonomies and the defined distortion, et cetera. Now we're able to do a lot more with, particularly with the new transformer models, and I'm going to show an example. From these distortion metrics, we're able to move, again, with the help of all of these pre-trained models, we're able to do embedding-based distortion metrics from graph coloring, actually hypergraph coloring, problem that was formulated then, automated clustering, utilizing, again, contemporary machine learning, and from our, modest simulated annealing approximations, of course, now we're able to do quite sophisticated neural networks. Okay, so exact reconstruction is no longer a requirement. What we want to do is simply convey the meaning. We can utilize semantic redundancy and context or side information, as however you wish to call it. We can utilize it for better compression. We can utilize semantic structures for better error correction. And our goal here is to ensure that we are satisfying the requirements of semantic metrics rather than simply syntactic ones. This kind of approach can pair well with task-oriented scenarios. If the receiver has a goal, all you care about is whether you achieved the goal or not. All you care about is you got enough good information to successfully complete your task, right? So let me give an example, right, of semantic compression for classification. Again, we're minimizing the semantic loss end-to-end. This is one transmitter and one receiver. And we're not even, don't even think about the channel yet. In fact, we're using completely separate channel and source coding in this approach. For the reason that, I guess this is as good time as any to mention this. If we want to introduce something brand new, we ought to kind of take it easy on the standards, right? So if we've done this for 50 to 60 years by putting a source coder followed by a channel coder, perhaps the best starting point is to try to, play with one and then keep the other and see if we get enough of an advantage. So the differentiator here perhaps is we want to leverage machine learning. We want to leverage all of these new advances, but we don't want to pay for the training costs that could come with autoencoder type fully deep learning based architectures. Okay? And that could be any cost that you can think of, energy cost or latency cost, as I will mention here. So our answer to that was to use pre-trained models. Of course, we're all now familiar with pre-trained models that have very large data sets that can train on specific generic tasks, rather. Such as predicting randomly masked words in some of the language models. And then you can do a fine-tuning, and you could do that perhaps at your communication system level with moderate resources needed. So I'm going to skip this. This was a large part of the previous talk. But essentially, all of these advances in large language models help in trying to think this way. Doesn't necessarily mean we're going to be deploying and training large language models at the edge, but that means that we can utilize the advances happening in that area, and a lot of things will continue to happen. Large language models are, in fact, in their infancy at the moment, and they're able to do quite a bit more. So anyway, so I'll give an example with this new, or relatively new, I should say, vision and language transformer model called CLIP. And we're going to use this pre-trained model to give an example of a multimodal classification-oriented semantic communications link. So this is a model where you put in, sentences or short paragraphs and pictures, and what it does is it takes them and it produces embeddings on a vector space. Embeddings are nothing but vectors, right? So basically, you put in the data, and it'll give you a bunch of continuous vectors. That's what it does. Okay? And they are close in the space, in this vector space, if they're close in terms of meaning, okay, which is what we're looking for. So we can utilize these embeddings to actually train a neural network for downstream tasks, such as classification, which we will do here, and use it for this task-oriented scenario. Okay? So the idea here is that we're going to have these embeddings at our transmitter, and then we're just going to send these embeddings. Right? And the classifier we have trained at the receiver end will do the classification based on the embeddings. So that's all great. And again, recalling that we want to do minimal changes, the first thing we should do is how do we make this a digital communication system? So we have the embeddings. What we need to do now is quantize the embeddings and then map them, send them as digital communication sequences. Okay? So we introduced two techniques here. One's a randomly chosen embedding from the data set as a dictionary. And then when a new sample size is being sample is being transmitted, we assign it to the closest index in our code book. And this can be optimized using a deep learner. The other one is to further provide efficiency by clustering similar embeddings together and then using the center as a code word and construct our code book that way. And this clustering could also be automated using machine learning, right? So it's basic techniques. And so, we have the transmitter, the receiver, the channel again, and we have a digital sequence. So the only thing that we've done from our classical communications block diagram is that we've included this pre-trained model in the encoder. Okay. But in the end, we have a digital sequence to send. We put in a standard Reed-Solomon, what have you. So the channel part is still separate from the source code. Okay, so I'm just going to show you some results. This is just the source coding results. And what I just want to point out, if you quickly take a look at, this is 5 different data sets, but we've tried it like in 14 different data sets, and we always get similar responses, which is by taking this semantic approach, we are getting 2 orders of magnitude in the number of bits. Okay, so that is something that is worth pursuing. When we put these into this approach into the wireless channel, we get reasonably similar accuracies in terms of performance in, let's say, typical SNRs like 10 dB. But what I want to show you really is this plot where we've defined a time efficiency metric where we're given a time budget, say, 1 second, whatever, your time budget. And the question we ask is, how many classifications can you do in this 1 second, in this time budget? And you see the advantage of these sort of mixing the pre-trained models with very small deep learners in this case, right? So we're able to do a lot more per unit time in terms of the tasks that we need to complete. And remember, that's what's important. We want to just complete the tasks with similar accuracy. Okay, so we've talked about communicating to execute a task. We haven't quite talked about communicating the meaning and then retrieving that meaning explicitly. So it turns out in that case, again, we can turn into contemporary machine learning architectures such as the attention layer, and it turns out it's actually quite helpful. So we tried it in now a 3-node network, so we graduated from 2 to 3 nodes, as we often do in communications, and this is a cooperative network, a cooperative relay scenario where we have suggested 2 methods. One is semantic lossy forwarding, and the other one is predict and forward. All right. I want to this is sort of very high level, but basically what you're doing is you're utilizing the context to decode at the relay, predict at the relay, and also decode at the receiver. I want to start, end with one thing. It was the importance of tokens was talked about, and I agree with that. And the previous one was, in fact, token-based communications. However, in our sort of hot off the press, most recent results show that instead of sort of tokenize and then really omit, I would say, the language kind of characteristics to a large degree, which is great when you have all the resources that you need and very, very large models, but not so much in a kind of a wireless scenario. You better try to find ways of using your sentences as your information units. So if you do that, you see kind of the difference of whether you need an embedding for each token or an embedding for each sentence, and the latter actually provides you with much better performance. So these are very, very recent results where we have looked into conventional metrics as well as a GPT-based metric that we basically asked ChatGPT, how good is this, right? And we see that utilizing sentences as your information units actually provides you with better system design. So in conclusion, I hope I've been able to convince you that 6G is the playground for the next wireless revolution. And the wireless design, if we include physical layer, can help improve collaborative learning performance, privacy, security, and we can have AI native designs in 6G, particularly in focusing on conveying the meaning. So I'll conclude by saying it's time for connecting with purpose, and hopefully for the students and researchers, junior researchers in the audience, hopefully these will resonate with you. There are lots of open questions in all of these, and hopefully you'll take those up and do wonderful things. And with that, I'd like to thank you very much for listening.
Thanks, Aylin. Thanks, Aylin, for first-hand research information and the results. Thank you very much. So we have some quick questions. Yes.
Actually, I have
You just talk. It's good. It's fine.
Okay.
Yeah.
So I have a very quick question. Thank you, Professor Aylin, for your presentation. It's quite remarkable. Okay, so my question is very simple. So we are talking about intelligent 5G or 6G, and currently we are talking about intelligent 6G. So, but for me, if we say something is intelligent, and then, for example, if we say people is intelligent, and then it's maybe because the people can do better decisions compared to the other people. But currently, I think for the intelligent system, we fit some machine learning models or machine learning methods into the network and can solve some problems of the network. And we also do some resource allocation or resource management to improve the learning performance. But actually, I think it's kind of not the real intelligent network. So I think my question is, what do you think is the biggest challenge to realize the real intelligent 6G or 7G systems? Thank you.
Thank you for the question. It's a valid question. I'm going to say baby steps, right? So taking a look at the system, sort of really taking a step back and trying to see how we should do the design, rather than, as you mentioned, taking a technology and sort of applying it to a communication system. I think that's the first step. But what I'm talking about with intelligent network is nowhere near human intelligence or any, sort of honestly, I know it's super challenging, but I don't need a robot to bring me coffee, right? So if we can actually get to a point where we have an industry, however, 0.0 that actually, or 0.2, that actually can do things that can make decisions that would, let's say, reduce the human's exposure to something harmful in an industrial environment, then we will have achieved it. Whether we can do it in 7G is yet to be seen, but I think we need to first come to a point where we can design wireless systems intelligently in terms of doing what they need to do in the wireless medium, and then really augment human intelligence to it. And I think we're somewhat a ways from it.
Thanks, Aylin. We have one more question, and then we take a photo.
Yeah,
Thanks.
thank you for the wonderful talk. Yeah, I have a question from the semantic communication part of your presentation. Like, in semantic communication, we intend to transmit only some relevant information only. So I just wonder, like, it might come up with some performance trade-off, performance loss trade-off. So, like how challenging that trade-off will, make it possible to bring this semantic communication into the standards.
Perfect. Yeah, great question. So I'm going to separate a little bit. So I have a rather specific definition for semantic communications, and that is to convey the meaning. So then your metric is how far away from the meaning, right? You can ask questions whether we have a, let's say, 100% metric for what that means. I'll be the first one to admit, not really, right? We are relying on some of the metrics that come from NLP that may or may not be as precise as we like it to be in the math world. But that is semantic communications. Sending relevant information or sending useful information, I want to classify as task-oriented or goal-oriented, right? And there, your metric is how correctly did I do this, or did I do it on time, or things like that are a little more sort of, let's say, solid in our minds. So there's a lot to do. I'm not kidding when I say there are lots of open questions in this, but I think this is how we start to think about these things, is what I was trying to say, if that makes sense.
Thanks, Aylin.